Okay. Let's see. We're just about ready. I'm just taking attendance, as I let you guys in. We'll do announcements and, I'll let you know what we're doing today. We are like down to the wire. Okay. Me. All right. So, got everybody in the waiting room. Let me mark these other gentlemen real quick. And we can kind of get the party started. I'm going to suppress my audio. So, as you guys come and go, let me get this other gentleman. Did I get him already? Yeah, I did. Okay. Okay. Let's see. So, this is. That's a good question. If exam 3 was what, week 12? So this should be the top of week 13, right? This is week 13. So what that means this week, what we're going to be doing, we're going to be starting on section 3.1. We only have two sections remaining of new material for the semester. We're going to focus on section 3.1 this week, which is on exponential functions, and then we have one more for next week. I think we do have the Thanksgiving holiday after these two sections, and that holiday, then we're going to be moving into the final. The main thing that I want everybody to be aware of, I'm going to suppress my audio. Main thing I need everyone to be aware of is that the access to old assignments locks out that Monday going into that first Monday of December. So it's like that, whatever that first Monday at 9 a.m., you can't access any of the old stuff past that point. The idea is that the final exam, we want the final exam to be the last thing that we do. So when you take the final, you're done with our class. Like there's nothing lingering. There's not all these, you know, outstanding assignments that we're trying to get caught up on. No, when you take the final, we want that to be it. And we'll talk more about the final as we get closer. Probably, as we get closer, like that Monday before Thanksgiving or whatever. I am monitoring the chat, so if you have a question, just get my attention. And we're going to go ahead and get it started with the topic for today with section 3.1. Is this thing lagging? Let me check something real quick. It feels good over here. Okay, I'm not going to worry about that. So chapter 3 is only one section that we're going to do in chapter 3. This chapter is regarding exponential and log functions. And so we're only going to be working on section 3.1, exponential functions. Some objectives here: we'd like to define an exponential function. We like to graph exponential functions, develop formulas for simple and compound interest, understand the number e, graph the natural exponential function, and model with exponential functions. So see, these are some of the ideas that we like to cultivate in this presentation. So let's introduce what do we mean by an exponential function. It's let's go like this. It's a function f of the form f of x equals a to the power of x, okay? Where the a is some non-negative integer, right? Strictly positive. A is a positive number, and a is not equal to 1, right? Notice if a were 0, 0 to the power of anything other than 0 is what? 0, right? And then if a were 1, 1 to the power of anything is 1, right? 1 squared, 1 to the power of 3. So I think in the past, we may have seen like x squared, x cubed, x to different raised to different powers. Now we're going to explore numeric bases raised to some variable exponent, right? So because the variable is in the exponent, that's why these are considered exponential functions. Again, this is called an exponential function with base a and exponent x. So base a and exponent x, okay? The domain of an exponential is all reals. And just to kind of provide a little bit of context, say we were to consider the xy plane, right? So say this is positive x, this is positive y. The exponential function takes on this shape, right? The further you go off to the left, it gets like infinitesimally close to the x-axis. It gets really, really close, but it never actually touches here. It looks like it does, but if you zoom in, you'll always find space. And then as it goes off to the right, it blows up, y goes off to positive infinity. As you go off to the left, As you go off in this direction, y tends to 0. As you go in this direction, y tends to positive infinity. This is the basic shape of an exponential function, right? Okay. So that's just a little bit of context. We're going to keep going. So in this first example, we like to evaluate exponential functions. So given these different exponential functions, we want to plug in values and see what the output is. So for part A, it says let f of x equal 3 to the power of x minus 2. We're asked to find f of 4, right? I'll use blue for now. So if we're going to do f of 4, that's going to be what? 3 to the power of 4 minus 2, right? So that's going to be 3 squared, which is that one just happened to be 9, right? We're going to come back and check. Let's look at g of negative 2. So then g of negative 2, that's going to be, it says that it's negative 2 times 10 to the power of x, and x in this case is negative 2, right? So a negative exponent, what does a negative exponent mean? A negative exponent means it flips and becomes a fraction, right? So 10 to the power of negative 2 is the same as 1 over 10 squared, right? So this is the same as negative 2 times 1 over 10 squared. The negative exponent turns it into a fraction. 10 squared is 100, so 2 over 100 reduces down to 1 over 50. Okay, and we'll come back and check all of these momentarily. We should be streaming. I think the stream is healthy. It looks okay. I'm not going to worry about it. Okay. So next we want to find h of x equal to 1 over 9 to the power of x, where x is a negative 3 halves, right? So h of negative 3 halves, that's going to be 1 over 9 to the power of negative 3 halves, right? Let me think about that. So a fraction in the exponent, that's really a radical. Like that power to the power of 1/2 is the same as square root. So we can work this in the following way. This is the same as 1 over, right? Because of the negative exponent. That power of 1/2 is going to be the same as the square root of 1/9, right? And then we can say that answer to the power of 3. Okay. We'll kind of go a little bit deeper into that to make that more clear. Square root of 1 over 9 is what? 1 over 3. So then this is going to be 1 over 3 cubed. So 1 over 3 times 1 over 3 times 1 over 3 is 1 over 27. So then 1 over 27, ultimately that result should be 27, right? Let's just see, we're going to kind of see some other ways of doing this. And we'll clean all this up. The last one is let f of x be 4 to the power of x. Now if we want to do f of 3.2, so f of 3.2 means we're doing 4 to the power of 3.2. I would just use the calculator. Right? Okay, let's see how do we do on these others. So we got our 9. Yeah, so a negative 2 over 100. We put 1 over 50, which should be the same as a negative 0.02. Let's see how did they do this. So now, with this one, h of negative 3 halves, right? The negative 3 halves was the exponent. So, okay, they rewrote this guy. 1 over 9. 1 over 9 is the same as 9 to the negative 1, right? Because we just said if a negative exponent moves it to the denominator, then the reverse is also true. If it's already in the denominator and you want to move it up, then it becomes, that's where that negative exponent comes from. So then here, when you say a power raised to another power, you multiply those numbers, right? A power to another power, we multiply. So negative 1 times negative 3 halves is a positive 3 halves, right? So then this is basically like a double negative became positive. Square root of 9 is 3. Again, this 2 in the denominator is the same as square root. So square root of 9 is 3, and then 3 squared gives us 27. So we saw 2 different ways of doing the same thing. And again, for this last one, I would just use the calculator. Okay. All right. That was an adventure. So I'm doing my best. Like I don't look at these things in advance, but I'm doing my best to have a clean stream so that because then I intend to use the video for the rest of the day. Like play it and just be available for questions instead of repeating myself all day. That gets old fast. Okay, graph this exponential function. Okay, so the suggestion here is to make a table of values, right? So we just chose these x values and we're going to find the corresponding y's. I'm going to work backwards. I feel like that might be a little bit easier to see. So for instance, when x is 3, we're going to have 3 to the power of 3. So 3 times 3 times 3 is 27. So when x is 3, y is 27. Right? When x is 2, y is 9, because 3 squared is 9. When x is 1, y is 3. When x is 0, 3 to the power of 0, that's by definition. 3 to the power of 0 is 1. Okay. So now, when x is negative 1, so 3 to the power of negative 1 is going to be 1 over 3. 1 over 3. 3 to the power of negative 2 is 1 over 3 squared, so that's going to be 1 over 9. Hopefully you can see the pattern now. So the next one should be 1 over 27, right? So with these x values, we just chose these x values and we found the corresponding y, and then we just plot the points. So if we plot the x versus the y, right, this is what we just did. And then if we plot the x versus y, we get an image like this. Remember, when we first opened up the section, I said that the general form of an exponential, you see it here, right? As you go off to the left, it gets infinitesimally close to the x-axis, which is like y equals 0. It gets really close to 0, but it never touches. So the x-axis serves as what we call a horizontal asymptote, right? An asymptote is a line that in a long-term behavior, you get close to that line, but you don't cross or touch it. It looks like you're touching, but if you were to zoom in, there's actually still space. That's the concept behind an asymptote. And then going off to the right, y goes off to positive infinity. Right? There's no asymptote on the right-hand side, but there is a horizontal asymptote for this. Okay. So the graph is this graph is typical for an exponential function when the base of a is larger than 1. Okay. Again, so this is an example where the base is larger than 1. Okay. So now let's look at an example where the base is between 0 and 1. Right? So then we're asked to sketch the graph of y equals 1/2 to the power of x. Right? So then again, we just chose some x values. We're going to find the corresponding y. So we can kind of use a similar technique to what we saw in the 2 examples ago. For instance, if we had 1/2, here, let me just write it here. I'll just write one of them. If we had 1/2 to the power of -3, right? We can do something similar to what we saw earlier. We can rewrite that 1/2 as 2 to the power of -1 to the power of -3, right? We just rewrote the 1/2. And then a negative raised to the power of another negative, it's like you multiply and it's like double negative, right? So then this is going to be the same as 2 to the power of 3. So then that means 2 times 2 times 2 is 8. All right? Okay. So this first one, the result is 8. Okay. What do you think the second one is? If x is -2, 1/2 to the -2 with the same logic should ultimately become 2 squared. It should be 4. And then 2, 1. Now, if we have 1/2 to the power of 1, any number to the power of 1 is what? Itself. So 1/2 to the power of 1 is a half. 1/2 squared means a half times a half, which is a quarter, and then an eighth, right? Hopefully you can see the pattern there as well. Okay. So we just we chose some x values, we found the corresponding y's. Here's a type version of what we just did. And then if we plot the points, now this is how the graph is changed when the base of the exponent is between 0 and 1, right? We call this like exponential decay. Because as we trace it left to right, it goes down. So the graph tends to 0 as we go off to the right in this case, and as we go to the left, y tends to positive infinity, right? So basically what's happened here is that the graph has been reflected over the y-axis. It's been flipped horizontally. So instead of having exponential growth like our bank accounts are about to do, all of our bank accounts are about to do, prophesizing, we now have exponential decay because it flips horizontally over the y-axis, right? Okay. So this is kind of interesting. I'm going out of my way to try to not use like ums and likes and stuff like that because I'm streaming. And as I say that now, as if they all come in floating in at once. But when you're doing presentations, you do the best you can to not use those like thinking filler words. So anyway, just random. Okay. So here, let me see. Here we have properties of exponential functions. So let let f of x equal, we have an exponential function, f of x equals a to the power of x, again, where that base a is positive and not equal to 1, right? So it's strictly larger than 0 and it's not equal to 1. Then the domain of the exponential function is going to be all reals, right? So that's why I was kind of showing, I wanted to show the graph right here, right? So the domain in a graphical sense is the very left to the very right. So what the domain being all reals means that every x is accounted for. For every x on the x-axis, we can find the corresponding y, right? So every x corresponds to exactly one y, right? We don't have one x corresponding to two y's. That was like one of the first things that we talked about in this course. Okay, right here. So again, the domain of the exponential function is all reals. The range is the very bottom to the very top. Remember how we said the graph has a horizontal asymptote? It gets really close to the x-axis, which is y equals 0. So the very bottom of the graph is y equals 0, and the very top is positive infinity. But we don't actually reach 0, so that's why we use the parentheses. So the range of the exponential function is from 0 to infinity, the open interval, right? We don't actually reach the 0. So the entire graph lies above the x-axis, right? Okay, let's keep going. So let's see. If we're considering the exponential function, if we take f of x divided into the next term, right, x plus 1, or not next, just f of x plus 1, this is going to be, so if we're considering the exponential function and we consider f of x plus 1 divided by f of x, then this is going to be a to the power of x plus 1 over a to the x. Since these are exponents of the same base, we can subtract the exponents, what they decided to do was factor it and cancel. If we said this exponent minus this exponent, the x's would cancel and we would be left with a to the power of 1, right? So the f of x plus term divided by the f of x term yields us a. So the y value is changed by a factor of a every time x changes by 1. So what this was showing was how the y values change as x changes by 1. That's it, right? So y changes by a factor of a as x changes by 1 unit. When the base is larger than 1, the growth factor is a, because each y value increased by a factor of a for each unit increase in x, right? So when that base is larger than 1, the growth factor is a, right? How much it's going to grow by is a. F is an increasing function, so when we look at the exponential function as increasing, what we mean is as we trace it left to right, is always going up, right? So f being an increasing function, the exponential function being increasing, means as we trace it left to right, it's always going up. So it rises to the right. As x goes off to the right, y goes off to positive infinity. As x goes off to the left, y goes to 0, right? Those are properties of exponential. Let's see what else we got. So now when the base is between 0 and 1, now instead of having exponential growth, we have exponential decay. So the function decays in this case by a factor of a, right? When the base is between 0 and 1. Okay. So then we say f is a decreasing function. So that was like the second one that we saw. But when we trace it left to right, it's going down. It's always decreasing. As x goes off to the left, y goes to positive infinity. As x goes off to the right, y goes to 0. Okay? So then we have each exponential function f is 1 to 1. 1 to 1 means that every x corresponds to exactly 1 y. You don't have 1 x corresponding to 2 y's, right? So every x corresponds to exactly 1 y. So given two different y values, then that should guarantee that means that we'll have two different x values, right? You don't have two different y values corresponding to the same x, right? And then another thing about exponential functions, we never really officially talked about inverses, but we're going to say that f has an inverse function. Trying to think of the simple way. I think in College Algebra 2 we'll talk about that. The graph of exponential has no x-intercepts. Again, remember, it never reaches the x-axis. It tries, but it never gets there. So it never crosses the x-axis. No value of x will cause the exponential function to equal 0. The graph of an exponential function is a smooth and continuous curve, and it passes through these three key points. Basically, when x is -1, we get this something like this. When x is 0, we get something, and when x is 1, we get something, right? So in a general sense, when we work with exponentials, when x is -1, 0, and 1, that'll give you a general idea of how this function is behaving. Is it like monotone increasing? Is it decreasing? Is it upside down? Like when x is -1, 0, and 1, generally speaking for exponentials, it gives us a lot of information about how this exponential is behaving. If we have exponential growth or exponential decay, stuff like this. From parts 4.3 and 5.3, we conclude that the x-axis is a horizontal asymptote for every exponential function of this form, right? So we kind of talked about that in the sense that, you know, for the exponential growth, as we go off to the left, it gets close to the x-axis but never crosses. For exponential decay, as we go off to the right, it gets close to the x-axis without crossing. And we talked about what a horizontal asymptote is, like a few minutes ago. The graph of y equals a to the negative x, so we introduced the a inside the base function, a negative inside the base function. So that's going to cause a horizontal change, right? From transformations, it's going to flip horizontally. So it's going to reflect about the y-axis of the graph of the regular exponential, right? So I know that's kind of a mouthful, but that's just an overview of like properties of exponentials. I feel like a lot of these naturally come out as we start working different examples. A few more terms and definitions. So one major application of exponentials is interest. So I think I'm going to take this time for quick story time. I don't know how quick it is, but I do want to have a little bit of a story time with this concept. Okay. And I haven't told the story in a while, so we're going to see how it goes. Let's see. So there's a story of the man who invented chess, right? This is like, I don't know, in the Middle East somewhere, I think it's something like that. But this man, you know, he invented chess, and he took his invention and he presented it to the local ruler. And so he showed him the game of chess. The local ruler was so pleased by his invention, he decided to reward the gentleman his weight in gold for his invention, right? So then the inventor thought about it for a moment, and instead of just taking the reward, the inventor decided, well, instead of just giving me my weight in gold as a reward, the inventor suggested the following. Okay, let me do some graphic. So the inventor suggested the following. So he said, like, on the first tile of the chessboard, we'll do 1 grain of wheat, right? So the chessboard is like 8 by 8, right? Let me see how quickly I can do this. 1, 2, 3, 4. So maybe if I like double it up, copy. I'm just making a chessboard. 1, 2, 3, 4. Copy and paste. Hopefully I'm having enough space. 1, 2, 3, 4. Let's see. 1, 2, 3, 4, 5, 6, 7. We're gonna need one more. 8. 1, 2, 3. All right. And then we do the same thing going this way. We wanna copy, paste. Only thing is, let me see if I have enough space. 1, 2, 3, 4. It's close. So what I'll do like this. Can you generate just a little bit more space? Move it like here, right? Okay, let me see if I got 8 by 8. Hopefully we have 8 by 8. 1, 2, 3, 4, 5, 6, 7, 8. Cool. Okay. So then we can do something like this. Okay. That looks good. I'm just making a chessboard. And then let's copy, paste, and let's go a little bit faster. Copy, paste, and paste. Okay. And then copy, paste, wait, undo. Copy, paste, and we want to rotate it. Boom. Okay, that's good enough. Okay, some of them are a little off, but it's okay. Okay, all right. So we got a chessboard, an 8 by 8 chessboard, right? So what the inventor suggested, he was like, okay, instead of paying his weight in gold on the first tile, he wanted like a one grain of wheat, and then on the second tile, he wanted to double it. He wanted 2 grains, and then on the third, he wanted what? Double that, which is 4, and then double that, which is 8, and then 16, so on and so on and so on, right? Until he filled the entire chessboard. The ruler thought about his proposal for a moment, and then he agreed to it. Right? Let's just see what did they both agree to, and what did they get themselves into, right? So let's see how much did the ruler actually agree to. Let me add another page. Let's do seamless. Okay. So what is it? What did the ruler agree to? Okay. So on the first tile, so let's let n be the tiles. On the first tile, let me see. We'll say grains. It was 1 grain, and we'll say the total. The total is what? One grain. Total grains of wheat. All right. Let's see. On the second tile, let me rewrite this. On the second tile, he was going to do what? 2 grains of wheat, and it's going to be a total of 3 grains, right? So on the first tile, if he does 1 grain, notice that that's equal to I think it's 2 to the power of 0, and then let me come back to that part. This is what? 2 to the power of 1, and then this is equal to 2 squared minus 1. This is equal to 2 to the power of 1 minus 1, right? Let's look at the third tile. He offered what? 4 grains of wheat, which is what? 2 squared, because if you double the previous. And now the total is what? 4 plus 3, which is what? 7. Notice that 7 is going to be 2 to the power of 3 minus 1, like this, right? So then now let's fast forward. Now that we kind of have a sense of the pattern, if we fast forward, let's jump to the 64th tile, right? So on the 64th tile, it should be what? 2 to the power of 63 grains of wheat, and the total grains of wheat on the chessboard are going to be 2 to the power of 64 minus 1 total grains of wheat, right? So the number of grains on each tile is going to be what? 2 to the power of n minus 1. And then the total number of grains at any given point is going to be 2 to the power of n minus 1, like this, where that minus 1 is outside the base function. All right, hopefully this is okay. So when you crunch that number 2 to the power of 64 minus 1, it ends up being something like, I mean, we can just do it. Let me just do it real quick. I'm going to crunch that number from the calculator. It should be ready. Let me see how quickly I can get my calculator going. And there's a little bit of a interesting ending to the story. I don't know if you know what it is or not. And I don't even know if it's true. It's just a story. All right. Let me reload and refresh. Come on. Okay. So now when we say 2 to the power of 64 and then minus 1, the result that we get, okay, we get this number. We get, it should be 18, comma, 44446, comma, 744, comma, and then this is as far as my calculator can go. Let me see. 1,000 million billion. Let me see. 1,000 million billion trillion quadrillion. I think it's quintillion. I think that's right. Let me see. 19. Let me check one. Let me check real quick. 3, 6, 9, 12, 14, 16. Let me see. 1,000 million billion trillion quadrillion. Why do I feel like I'm missing something? It's basically. Oh, we got somebody in the waiting room. Let me get him real quick. Let him in. It's supposed to be 18 quintillion. Let's think if I'm doing this right. 18 quintillion grains of wheat. I think that's right. Let me check it one more time. Let's see, if the decimal's here, that's 3, 6, let me see. 3, 6, 9, 12, 15, 18, 19. Yeah, this is right. So, and this is approximately, right? So what we're saying is that the ruler agreed to pay approximately like almost 18.5 quintillion grains of wheat. This amount of wheat would fit just inside. I think it was like a thousand. I think it was 1,000. Oh, was it 1,000 miles or 1,000 feet? I can't remember the size. I think it was. I think it was. I think it was 1,000 feet by 1,000. It was either 1,000 feet by 1,000 feet by 25 feet, and that makes more sense than 1,000 miles, right? I think that was the size, but it was a large silo, like it was either 1,000 by 1,000 by 25 feet or 1,000 miles, but 1,000 miles sounds ridiculous, right? But it would just fit inside a large silo. This amount of wheat is more wheat that's ever existed in the world, right? So the conclusion of the story was that the inventor actually tricked the ruler into paying way more than what he could afford. He was trying to trick the ruler out of his fortune or whatever. And so when the ruler realized that he couldn't pay the man, you know what he did, right? You know what he did to the guy, off with his head. Yeah. At least that's how the story goes. Again, it's just a story. I don't know how much of it is true. It's just an interesting, fun way to kind of to talk about exponential functions, right? So that was the conclusion of that story. But the thing here was just showing how things can grow exponentially, right? Starting with a simple concept. Let's go paper, and just how quickly things can grow, right? So that was just a demo on exponential growth. Let me put this back. Single page. Okay. Right. So that was just introducing a concept of exponential growth. I say we have like about a little over 5 minutes. Let me make sure this is right because I see it's also freezing. Okay. So I'm going to keep going. I'll let you guys out in just about 5 more minutes, but I'm gonna kind of keep going with some of the concepts, and then I'm gonna let you out. I'm gonna keep streaming just because I want one clean, smooth stream of this concept, and then we'll go from there. So with this next concept, we have interest rate, and so we're taking the concept of exponents and exponentials and exponential functions and applying them to finances. Right, so we have the interest rate is a percent change for the use of the principal for a given period. The interest rate denoted by R is expressed as a decimal. Unless stated otherwise, the period is assumed to be 1 year. That is, R is the annual rate of growth. The amount of interest computed only on the principal is called the simple interest. Actually, there's another story. And I think I'm going to just go ahead and tell it since I'm streaming and I can kind of fudge time a little bit. So when I was a student at Morehouse, I went to, there was this like honor society, like it was a meeting. And one person came up and did a presentation, and they were asking for donations because they were doing a fundraiser for something called the Infinite Scholarship. And we were like, what? What's an Infinite Scholarship? And so this is a short story. So the Infinite Scholarship at that time, and I'm pretty sure it still exists to this day. I haven't found accounts that behave like this, but I know they exist, right? So the Infinite Scholarship goes like this. You get an account where the principal, a starting amount of $1 million, right? So say you had an account, you had $1 million to put into an account. And this account earned at least 5% simple interest, the lowest form of interest there is every year, right? 5% interest added every year. So then the idea is that if you have $1 million and you have an interest-bearing account that earns 5% every year, how much money does that account earn every year? All right, what's 1 million times 0.05? So if you start with 0.05 and move the decimal to the right, what, 6 times? So if we go 1, 2, 3, 4, 5, 6, right? So what we're saying is that if you have $1 million just sitting in an interest-bearing account that earns 5% every year, that's the lowest form, simple interest, the lowest form of interest. That account just by itself earns $50,000 a year, which is a full-time check, right? That's like a couple of thousand a month, right? So, and I'm sharing this because I know some of you guys are going to come across this. You're going to be able to do this. Like somebody's going to have $1 million and they're going to have access to $1 million account. So what this means is that every year this account generates $50,000 just for sitting there. So as long as you don't spend more than $50,000, again, a couple of $1,000s a month, as long as you spend less than $2,000 a month, you just get $2,000 every month forever, as long as that account is open and active, right? That's the Infinite Scholarship, and people do this. Like this is honestly what my dad showed this to me when I was younger. And we kind of fell off, but I'm still aware of it. I'm just trying to get to those credentials. I know people that have had this amount of money. I don't know if they were aware about interest, compound interest, and interest-bearing accounts. But if you put these two together, you can earn $50,000 a year, which is you can find decent living for that amount every year. And so as long as you only touch the interest earned and don't touch the principal, you get that money coming in forever. So that's the Infinite Scholarship. Okay, so I have that it is the end of class today. I'm not going to keep any of you past this point. If you made it into my Zoom, I went on and gave you attendance credit. What I'm going to do, I'm going to go ahead and finish out this section. I think I'm about halfway, so you're welcome to stay if you like, but you're not required to. All right, guys, I'm going to keep going, and otherwise we'll pick this up. I do expect you to watch this on your own, take notes as if you're in class, and on Wednesday we'll work some of the problem set associated with this. Okay, so the amount of interest computed only on the principal is called simple interest. That was what you saw me do with the Infinite Scholarship. So the simple interest formula, the simple interest I earned on the principal P at a rate R expressed as the decimal per year for T years is this, right? So given some account where the initial deposit is your principal, which is P, the annual rate of growth, which is your R, and the time in years, this is how you calculate simple interest, the interest earned on an account with those conditions, right? So in this example, we have that Juanita has deposited $8,000 in a bank for 5 years at a simple interest rate of 6%. How much interest will she receive, and how much money will be in her account at the end of the 5 years, right? So for part A, how much interest? So the simple interest, I equals PRT, right? That's how I remember that. So this is going to be her principal was 8,000. That's what she started with. The rate is 6%. The percent we have to express it as a decimal. So 6% as a decimal is 0.06. Let me see. And it says 5 years, so the time is 5 years. Time is generally in years when we're doing these compound interest formulas. So 5 years, right? So then if we say 8 times 0.06 times 5, let me see. 6 times 5 is what? 30 times 8 is 240. I think it's like if we did 240, 2.4. Let me think about it. It's not 20. I think it's let me see. I know the number is 24. And when I say, if I just do a straight 6 times 5 times 8, that's 240, right? We should bring the decimal back by 2, but then up by 3. 1, 2, $2,400. Does that make sense? Let me see. 5 years, 6%. Let me see if this is correct. 2,000 is either 2,000. Yeah, we're good. Okay. I don't know why I was doubting that number, but I was. But anyway, that's okay. So yeah. Now I didn't show the nuances there. You can use your calculators, and I didn't write everything out. I was just jumping to the answer, right? If I need to go further in depth, I can. But yeah. And then how much money will be in her account at the end of 5 years? Oh, so then for the future balance or the future amount, that's going to be her starting amount plus the interest earned, right? So that's going to be the 8,000 plus the 2,400 earned. It's going to be what, 10,400? So we just took that result and added it to her starting amount. That's if she just lets it sit for 5 years. Okay. Okay. I think we're good on both of those. 2,400, 10,400. Okay. So then now what we saw just a moment ago was a demo on simple interest, right? The lowest form of interest. There are levels to this shit, right? That simple interest is the lowest form of interest. So that's where the interest is applied once in a year. So then this next concept is called compound interest. It's going to be the interest paid on both the principal and the accrued amount previously earned interest. So interest that is compounded annually is paid once a year. For interest compounded annually, the amount A in the account after 2 years is given by this, right? So basically, like if the interest is applied once per year, this is like the future amount if you take the principal plus the simple interest, you get something like, you get this, right? Let me see if we go further in that. Okay. Is this the same one? She has the 8,000, 6% annually, 5 years. We did that one. How much interest will she receive? Oh, compounded annually? Okay. So if we use the compound interest formula, right? It's going to be P times 1 plus, it's usually R over N, R to the power of NT, right? So this is if the interest is applied once in a year, right? Okay. So this, I'm just using the formula that was on the previous slide. Again, the principal is 8,000, 1 plus the rate as a decimal. 6% as a decimal is 0.06 times 5 years. This is the interest earned that's applied on top of the amount, on top of the principal that was already there. So then we use our calculator, right? This would be 8,000 times 1.06 to the power of 5, right? We just use a calculator. I'm going to leave it there and just know that we're using a calculator there. And then part B, how much interest? So whatever the answer is, we're going to say, I'm going to abbreviate it as that answer minus whatever minus the 8,000, all right, to get that part. Okay. So let me see at least, so you see it here, this is where we stopped, 8,000 times 1.06 to the power of 5, and you put it in the calculator, you get this. And then the interest earned was whatever the answer was minus her starting amount, right? And we get this, okay? So I just wanted you to see the concept there. Let's try another one. Now that's not the main compound interest formula that we use. That's why I was kind of like I stammered a little bit. because I kind of use this one. This is the one that whenever I'm doing compound interest, this is the one that I go to. This is the same as what we had before. It's just that in the previous example, we applied the interest once per year. Now this is where suppose we apply the interest multiple times per year, right? That's what the n is for. So this is the compound interest formula. And then also there's actually, I mean, we could go into the details of where these formulas are coming from, but just for the sake of time and, you know, your sanity, and it's not that difficult to go into it, but I'm gonna leave it for right now, right? But we can at least kind of talk about what these different components are, right? So the A is the amount after t years, the amount in the account after t years. The P, which is your principal, is the starting amount. The R is your annual interest rate. Again, we have to express that as a decimal. These n's are the number of times the interest is applied in a year, right? So if the interest is applied annually, that would be a 1. If it's semi-annually, that'd be a 2. If it's quarterly, it would be a 4, so on and so on, stuff like that. And then t are the number of years for this account, right? So this is the one. I'm being a little bit lazy. I'll do a few of these. So say we have $100 is deposited into a bank that pays 5% annual interest. Find the future value A after 1 year if the interest is compounded. So now for the first one is annually, then semi-annually, quarterly, monthly, daily, so on, all right? So we're using a compound interest formula. That's going to be A equals P times 1 plus R over N to the power of NT, right? So for the first one, let's see, say the interest is annually, right? I'm gonna abbreviate it as A sub 1 so we know that we want the amount. It's going to give us the amount if the interest is applied annually. The principal is $100. 1 plus the rate is 5%, so that's going to be 0.05. I'm going to come back to that annually part. N and the T is 1 year, right? So we can just make that at 1 right now. This is what we're doing with each step. Copy. Okay, so each step, and then the only thing that's changing. So if it's annually, then our n is 1. Our n is 1, and this is actually a 1 as well, right here, right? Our n is 1. I would just use the calculator to crunch these numbers. I'm just going to show you where these are coming from. 1, 2, 3, 4. I need 4 more. So let's just do them really quickly. Paste 1, 2, 3, 4, right? So then semi-annually means that the n is 2, the interest is applied twice in a year. Quarterly, n is 4, it's applied 4 times per year. Monthly, n is 12, this is applied 12 times per year. Daily is 365, interest is applied every day. All right, we will use our calculator to crunch these results. So I'm just going to say, hey, use a calculator to get these results, and I'm going to use my next slides. Here, instead of that, let's just do it like this. I was going to separate them, but I can just match the size, and that'll work, right? Okay, so I would say just use the calculator to find all those results, and then but we've done that already, so now let's see it here. So say the interest is applied once per year, then the amount at the end of the year is going to be $105. Say it's applied semi-annually, so now we got $105.06. Now say we apply the interest quarterly, like every 3 months, 4 times in a year. Then now we got 105.09. Then it's 12, and then it's 13. So what do you notice about the more compoundings we do in a year? What are we noticing with the amount in the account at the end of each year, right? It seems like the more compoundings we do per year, the more of a return we get. Remember I said that like simple interest is the lowest form of interest that we have. this is what I was referring to. The more compoundings we do, the more return we get. All right. So, right. So these were like discrete compoundings, where in the sense that, you know, these are countable numbers, right? This is like once a year, twice a year, 4 times a year, stuff like that, right? So then, what if we were able to just always be applying the interest? Like that's called the continuous compound interest formula. So if we took the limit as n went to infinity, right? So we saw where n was 1, 2, 4. I think we had 12, 365. So then what if we let n go to infinity? The interest is always applying to this account. So then that takes us to this one, which is the compound interest formula. So then it's a different formula. Whenever the interest is applied continuously, which is the highest form of interest that at least I'm aware of, at least for our discussions, is a continuous compound interest formula. A is going to be the future amount. P is still your principal. R is the rate of growth, written as a decimal, and T is the time in years. Because we're doing continuous, this E is like a function in the calculator. It's kind of like pi, it's just a function in the calculator, right? So it's not anything you're going to fill in. It's like 2.73. It's something in the calculator, and it basically comes out of calculus. Like I think if you had an account that has like $1 and you gain 100% interest, and as you take more and more compoundings per year, as the n goes to infinity, the return on the account approaches the number 2.73, right? And so they call that number E. That's where that comes out of, right? To try to keep it as simple as I can as far as explaining that. But for our purposes, that E is just a function in the calculator, right? So then here, in this example, we're asked to find the amount when the principal of $8,300 is invested at 7.5% annual rate of interest compounded continuously for 8 years and 3 months, right? Okay, let's list out some of the things that we're given here. Now, it says compounded continuously, so when you see continuous compounding, then we're using the PERT. I call it PERT, A equals P e to the RT, PERT formula, right? We're trying to solve for A. Our principal, the given P, we're starting with $8,300. The rate, again, we have to express it as a decimal, so 7.5% as a decimal, 0.075. We have to convert it. Basically, you divide by 100. So you move the decimal to the left twice. The time, again, time has to be in years, but they gave it to us, it says 8 years and 3 months. So we need to convert that 3 months to years, right? So the time is going to be let's see. Let's do the conversion really quickly. So if we have 3 months and we want to convert it to years, how many months in a year? 12 months corresponds to 1 year, right? So when we're doing conversions, we put the units opposite so they cancel, all right? You want the units to cancel. So the units of months here cancel the units of months here, and we're left with our desired result of years. 3 divided by 12 is what? 0.25. So then 8 years and 3 months is 8.25 years, right? So we had to convert months to years and get all of that in terms of years. So now we have all the components. We just plug these into the formula. So then the future amount is going to be the 8,300 times e to the power of 0.075 times 8.25. At this point, you would just use your calculator, right? So I just wanted you to see that discussion. Principal was the monetary initial deposit. Rate has to be expressed as a decimal, and the time has to be in the unit of years for these formulas to work. If you don't do the conversions properly, they're not going to work, and you're going to be led astray. So you see the principal was 8,300. The rate was written as a decimal, and then we had to convert the 3 months to years. We got 8.25 years. Then you see the part where we stop. You use the calculator to generate that final result. Okay. So This next one is the natural exponential function, right? F of x equals e to the power of x. Has a base e. With the base e is so prevalent in the sciences that is often referred to as the exponential function or the natural exponential function. So this is a function that, if you do any kind of sciences, this is inevitable, right? So let's look at it. If we compare the natural exponential function where you have the base e to, say we compared it to y equals base 2 versus base 3, right? So the base e is between base 2 and 3, right? Because remember we said that e was 2.73 something, like it's this irrational number between 2 and 3 but closer to 3. So then that's why this graph is between the exponential function base 2 and exponential function base 3, right? But it still has the same general shape of an exponential. So base e, or the natural base, the natural exponential function is in red, which you see. Okay. So then we're asked to use transformations to sketch the graph of this, right? So if we take the base natural exponential function that we saw in the previous slide and we apply transformations, right? So hopefully you can see the transformations. There are two transformations that we've talked about in this example. We're using two transformations. The first transformation is that we subtracted one inside the base function, right? So subtracting subtracting a positive number inside the base function, that's going to cause a horizontal change. It's going to move it to the right by 1 unit, right? So this one says to move to the right by 1 unit. We added 2 outside the base function, so that says to go up by 2. So all we're doing is taking that generic exponential graph, we're going to the right by 1 and up by 2, right? And then that's the graph. That's it. So those are rigid transformations. It's just moving the position, and it's not distorting the image, right? So it shifts the graph 1 unit right and 2 units up. So you see the original in blue. If we go 1 right and 2 up, you see the transformed graph in red. Okay. So that's kind of bringing back basically the concept of transformations that we talked about earlier in the semester. And honestly, when I was a student, I never took college algebra. I started off in calculus, and so I had a decent base. Like I knew how to crunch the numbers, and whatever we talked about made sense. But I didn't know about transformations, and like there were some concepts here that we've talked about that I needed when I got to grad school, and I don't know why it just never dawned on me. I guess because I had never sat down and gone through a college algebra course until I taught it, right? I guess when I was in high school, we took algebra, but there does seem to be college algebra just has so much information. There's a lot. Like we cut half the information that we normally talk about. You guys got about half of it. So we split it. Instead of doing one semester of everything we think you need, we broke it into 2 semesters, right? So that's the current thing, which I think is better for everybody. You guys aren't stressed out, and we don't feel so bad about like the workload, because the way it was in the past, it was intense. It was intense. Anyway, so yeah, that was that. We're actually almost done. So then the last thing that we'd like to discuss is modeling an exponential growth or decay function. So given some a situation that is either exponential growth or exponential decay, can we create a model? So in the previous examples, we were given the model and we wanted to see how things behave. Now, given some conditions, can we create a model to get a sense of how a system is going to behave in the future, right? So this is the exponential growth or decay model, where A of t is going to be the amount present at time t. A naught is going to be basically the initial amount. It's like your p, right? So we're in the previous examples, we were calling this p. Now we're going to call it a naught, or the initial amount. K is the relative rate of growth if k is positive, or it's the rate of decay if k is negative. And then t is your time. So we often use this for like population growth, up until an extent. Let's look at it. Let's see it in action. So in the year 2000, the human population of the world was approximately 6 billion people, and the annual rate of growth was about 2.1%. Using the model on the previous slide, estimate the population of the world in 2030 and in 1990. All right, so assuming exponential growth. All right, So can we take this information and model it to the exponential function? So exponential, let me see. So we had a of t, it was a naught times e to the kt. I think that's what it was, right? And let's see. So we're going to let the year 2000 be like be the starting position, like t is equal to 0. All right. Okay, so in the year 2000, the population was 6 billion. So let's plug that in. So we're going to let, if that's two, let me see. So the starting amount was 6 billion. It says the rate of growth was 2.1%. We have to write that as a decimal, so that's going to be 0.021. Okay. If we're going to let the year 2000 be year 0, right? So we're going to let t be 0 there. I think this is okay. What am I missing? Okay, let me back up. Let me not do it just like this real quick. Okay. So for part A, right? We want the year 2030. So we're saying it's 30 years later, right? So we want to find A of 30. The starting amount was the year 2. We're still going to let the year 2000 be time t equals 0, which is the starting amount. So the population at that time was 6 billion people. The rate of growth that we're using is 0.021. And again, the time has been what, 30 years, right? So that's all the information that we need. Using the model on the previous slide, estimate the population of the world in these years, right? So then we have basically, so we plugged in the different components. After 30 years, right? After 30 years, if we started with 6 billion people in the year 2000 at a growth rate of 2.1%, and again, this runs for 30 years, at this point we would just plug it in the calculator, right? And then, so that's part A. And then part B, if we want 1990, and again, the starting year is the year 2000, then we would want A of negative 10. Again, the starting amount was 6 billion. E to the rate of growth is 0.021. But now the time is we're going to do negative 10. And then put that in a calculator. Okay? So I'm just going to leave the calculator parts as an exercise, and I'm going to piggyback off of this. All right? And I think you see all the stuff that we wrote out. So after 30 years, so we want the amount after 30 years. So started with 6 billion. The rate of growth is 2.1% for 30 years. After you put it in the calculator, it should put this out. So the model predicts the rate of growth is 2.1% per year over, if the rate of growth is 2.1% per year, over 11.26 billion people will be in the world in 2030, right? That's based on this modeling with those conditions. And then for the second part, see, it's the same thing. The amount 10 years earlier, based on this model, starting amount was 6 billion at a rate of growth of 2.1%, and 10 years earlier, in 1990, that the model suggests that there should be 4.86. Predicts that the world had over 4.86 billion people in 1990. The actual population in 1990 was about 5.28, right? So this is a model. We do the best to be as precise and exact as possible, but it's not. It's just not exact. All right. Let me see. Oh, okay. I think this is the last example. So we buy a fishing boat for $22,000. The boat depreciates exponentially at an annual interest rate of 15% of its value. Find the depreciated value of the boat at the end of 5 years. Okay, well, I didn't even realize this was there. We use the exponential decay model, right? The only difference here is still a naught e to the kt, but now since we're doing exponential decay, we need negative kt, right? So then the starting amount was 22,000. The rate of growth was 0.15, and I think it's 5 years, right? At the end of 5 years. And again, we have that negative because it's exponential decay. It's depreciating. Let's see. So then if we plug in the different components, if we want the amount, the value of the boat after 5 years, with this starting at being valued at 22,000, it's exponential decay. The decay rate is 15% for 5 years. You put it in the calculator, it outputs this, right? So the value of the boat at the end of 5 years is going to be $10,392.06 approximately. Okay. All right. So it wasn't that much more, maybe 20, no more than 30 minutes more than what we usually go that we wanted to talk about, right? So, it was a little bit rocky, but that was just us introducing concepts of exponential growth and decay and exponential functions. And so on Wednesday, on the next session, we'll take some time to work through some of the problem set associated with this presentation. Okay. And if there aren't any burning questions, on that note, we're going to end the session here. And from one beautiful mind to another, enjoy the rest of your day. Take care. Peace, guys.